Welcome, incoming master's students, to MENE 313. I'll be your host and guide for this introductory explainer today, where we're basically mapping out our entire semester's intellectual journey into the really complex but absolutely fascinating world of waste-to-energy systems. We're going to be diving into the foundational concepts and the conversion technologies that will essentially define your future work as environmental engineers.
Throughout this course, our main academic anchor is going to be the official MEN 313 course manual. It's titled Energy Engineering, Waste to Energy, authored by Engineer Val Irvin F. Mabayo. This text does a great job of synthesizing the basic concepts, the critical engineering considerations, and the technological pathways that we'll be analyzing together over the coming weeks.
Okay, let's dive into this with a quote straight from the manual. It says, "A technology is useful only when it is technically sound, environmentally responsible, and appropriate." I really want you to keep this cautionary, evidence-based philosophy in mind for literally every single system we evaluate this semester. Because, waste of energy isn't just about producing power, it's about making tough decisions that ultimately protect public health and the environment.
So here is our roadmap for the syllabus. Think of these as the distinct toolkits you're going to master. We start with waste characterization, then move into thermal conversion, explore biological conversion, analyze chemical conversion, and finally, we tie it all together with the engineering mindset.
Starting things off with Section 1, Waste Characterization. This is truly the foundation of all waste-to-energy design.
Before you even think about drafting a plant design, you have to establish the absolute golden rule of our discipline. The feedstock dictates the technology, never ever the other way around. As an environmental engineer, the very first thing you have to ask is simply, what exactly is the waste? A city might generate a literal mountain of refuse, but abundance alone doesn't automatically make a waste suitable for energy recovery. A massive stream of wet, inert, or heavily contaminated material? That might yield almost zero actual energy. We really have to know what we're dealing with first.
Now, what's really interesting about this slide is how these specific physical, chemical, and biological properties literally rule out or, conversely, support certain technologies. For example, if the moisture content is way too high, well, that might completely kill a direct combustion process, but it could be absolutely perfect for a biological one. The heating value tells you if you can actually recover useful thermal energy at all. And things like contaminants, chlorine, heavy metals, those are going to dictate your air pollution control costs. Your feedstock's properties basically make the big engineering decisions for you.
That brings us right into our first toolkit in Section 2, Thermal Conversion Technologies, which is all about using heat to transform waste.
This specific family of technologies is strictly meant for materials that actually have recoverable chemical energy and can be processed under highly controlled, high-temperature conditions. And it's so crucial to understand that modern thermal conversion is absolutely not just incineration. Let's break this down. Combustion operates with excess air to completely oxidize the waste, giving us heat, steam, and electricity. But then you have gasification, which uses limited oxygen or steam to produce a combustible syngas. Meanwhile, pyrolysis operates in the complete absence of oxygen to thermally decompose organic materials into bio-oil, biochar, and non-condensable gases. So each route has completely different feedstock requirements and outputs.
Just to put that into perspective and give you a sense of scale, a well-designed plant can generate up to 0.7 megawatt-hours of electricity for every single ton of municipal solid waste combusted. But remember our golden rule here. This number depends entirely on the calorific value of the waste stream. It's a potential target, not some universal guarantee.
Let's transition over to our second toolkit in Section 3, Biological Conversion Technologies, focusing on microbial energy recovery.
Let's move to and see how this builds, because if thermal conversion uses heat, biological conversion uses microorganisms. This toolkit is specifically tailored for wet, biodegradable organic materials. So think food waste, livestock manure, sewage sludge, that kind of thing. The core process here is anaerobic digestion, and it builds sequentially across 4 linked biochemical stages. First up, hydrolysis breaks down complex organic molecules into simpler ones. Second, acidogenesis ferments those products into fatty acids and alcohols. Third, acidogenesis converts those into acetic acid and hydrogen. And finally, methanogenesis steps in to generate the ultimate prize, methane. Now, if any one of these stages gets imbalanced, say if the pH drops too fast during acidogenesis, the whole system can literally crash. It's a delicate balance.
The end result of that delicate microbial balancing act is biogas. Typical biogas relies heavily on methane. It's roughly a 60-40 split on average, so 60% methane and 40% carbon dioxide, though it can vary from 50 to 70% methane depending on your specific system. The methane is the part that actually holds the energy value. The carbon dioxide is essentially just a diluent, and you might actually need to strip it away if you're trying to upgrade this to pipeline-quality biomethane.
And this brilliantly illustrates the core learning objective of our first few modules. Notice the stark contrast? Thermal feedstocks demand dry, combustible materials, and they really struggle with moisture. On the flip side, biological feedstocks absolutely thrive on wet, biodegradable organics, but they offer zero help if you're dealing with dry plastics or inert materials. Being able to differentiate between these toolkits is really step one of developing your engineering judgment.
Now we arrive at Section 4, Chemical Conversion Technologies, which is all about upgrading waste into advanced fuels.
Here, we aren't just breaking waste down for raw heat or gas anymore. We're carefully separating and upgrading really specific molecular fractions into liquid fuels and specialized chemicals. A prime example of this is solvent-based biomass conversion. This involves using specific solvents to dissolve, extract, and separate components like lipids from, say, microalgae for further chemical upgrading into biodiesel. But there is a massive green chemistry consideration here for us as environmental engineers. Chasing a slightly higher extraction yield is absolutely not worth it if you end up producing highly toxic secondary wastewater from harsh solvents like chloroform or methanol. We always have to balance the yield with environmental safety.
And chemical routes demand extreme feedstock control. For instance, used cooking oil targets triglycerides for biodiesel, but its high free fatty acid content can completely ruin your catalyst. Microalgae offers lipids, but the extraction process is highly energy intensive. Carbohydrate biomass gives us fermentable sugar, sure, but it requires really severe chemical pretreatment just to access them. So chemical conversion is incredibly precise, but it is deeply unforgiving if you have poor quality feedstock.
Which brings us to our final section, the engineering mindset, where we focus on developing cautious, evidence-based judgment.
So, the crucial point is that mastering the thermodynamics, the microbiology, and the chemistry, that's really only half the battle. The ultimate learning outcome for you this semester is developing a cautious, evidence-based engineering judgment, and that relies entirely on the standard operating procedure. Step 1, define the specific waste stream. Step 2, apply the waste hierarchy, meaning can this be reduced, reused, or recycled before we even think about burning or digesting it. Step 3, characterize the physical, chemical, and biological properties. And Step 4, only then do you match the pathway to the feedstock. It's like a giant puzzle. We always move from the waste stream to the technology, never, ever from a preferred technology desperately looking for a waste stream to justify its existence.
As you prepare for the semester ahead, I really want you to consider this. You're going to learn how to design combustion grates, anaerobic digesters, and complex chemical biorefineries. You will absolutely know the technologies. But the real question for an environmental engineer is, do you have the judgment to use them responsibly? That is exactly what we are here to build. Welcome to MEENE 313. I'll see you in our first deep dive module.